Today we're going to talk about refraction. Refraction is the word we give for what light does when it enters a new medium. Okay, so for example, when light is traveling through nothing, when it's traveling through the vacuum of space, it is traveling at what we would normally call the speed of light, right? Which we use the letter c for that, and it is 3.0 times 10 to the 8th meters per second. Okay. However, when light actually travels into something else, it will actually slow down. Okay. How much it slows down depends on what it's traveling into. Is it traveling into air? It slows down just a little bit. Is it traveling into water? It'll slow down even more. Okay. So we actually have a formula that dictates how much it'll slow down, and it's this right here. N equals C over V. Okay, let's say what all these things stand for. Okay, N right here is what's called our index of refraction. This value tells us of refraction. This value tells us how much the light is going to slow down when it enters this new medium. Okay, this value right here is always the value we plug in for C. And V is the new velocity in the new medium. Okay, so let's do a quick example. Let's see, how fast does light travel in water? Okay, so in water, V equals question mark. See if we can't answer that. Well, we're going to use the formula N equals C over V. Keep in mind that N is the index of refraction. So we're going to need to come up here to our table. There's one of these tables in your textbook for reference when you're doing your homework and stuff. We're going to need to use the index of refraction of water, which is 1.333. Okay? We're going to plug that in for N. C is going to be the speed of light, the 3 times 10 to the 8th that we always use. V is going to be the new speed of light in water. So before we plug in any values, let's solve for V. We're going to multiply both sides by V, and then we'll divide by N. So we end up with this right here. V equals C over N. So if we plug in our value of 3 times 10 to the 8th meters per second, we divide that by N, which is 1.333. Let's grab a calculator, see what that is. Should have grabbed one before I started this. All right. 3 divided by 1.333 is 2.25. Okay. So our new velocity in water is 2.25. Of course, it's still times 10 to the 8th, and that's meters per second. So this right here is how fast light travels when it enters into water. So it slows down quite dramatically from 3 to 2.25, so almost a third. Okay, so we could do this with any of these materials up here, and we could determine how fast light travels when it goes into this new material. All right, let's see what else light does when it travels into a new material. Don't save. Let's open up a blank canvas here. Okay. What happens when light travels into a new surface? Here we go. There we go. Okay. So, hang on one second. All right, there we go. There we go. All right. Actually, don't need that line quite yet. Give me just a second. All right. So, if we have light traveling into water, for example, Let's draw a line of water. Let's say the light comes in at this angle right here. Okay, this is our incident ray. Wow, that is not how you spell incident. Incident, there we go. Okay, you guys know how to deal with this. We draw the normal, we draw the perpendicular line, and we label our angle of incidence. And we know that it's going to reflect at that same angle. So this would be our angle of reflection. Okay, so this is the reflected ray. Okay, but it turns out that if this is water down here, let's say this is air, and this is water, the light is going to keep traveling, and it's going to go into the water from the air. Some of it. Some of it will reflect off the surface of the water. Some of it will go down into the water. It turns out that it's not going to travel in a straight line like you would expect. It actually bends somewhat. And we're going to, of course, label everything from the normal. So this is our new angle. So notice that it's turned and actually come to a smaller angle right here. So this is our angle of refraction. So this is our refracted ray. Refracted. Okay. So how do we predict how exactly it's going to turn? We know it's going to turn in a little bit because I just drawn it like that. But why does it do that? Well, let's take the example of a car. Okay. With a car, let's say you've got a car. Actually, let's do this in green. Over here, you've got some grass. And you're driving a car. Let's say you're driving a red car. Here's your car. And it travels at this angle, and it's going to hit the grass. So right now, you're up here on the road, and you're going to travel down here into grass. Well, let's say your car has 4 tires on it. Not the greatest tires, but go with it. Okay. It's going to come in at some angle. What's it going to do? Well, when it gets here, part of the car is going to hit the grass first. This side of the car right there is going to hit the grass first. So what's the tire going to do that's hit the grass? Well, it's going to slow down. So you're actually going to, this side is going to slow down, but this side is still going to be going the same way. So what's the car going to do? It's going to turn. And instead of traveling in a straight line like this, actually it's going to turn like that. So that's how we can think. Light is doing the same thing. Since the light, as it's coming in, is going to slow down when it hits the water, it actually turns in closer to the normal, such that our original incident ray is bigger than our refracted ray. Okay, so you can make predictions like that. Let's erase this. Let's see if I can erase this. How can I do that? Let's do that with this tool. See what happens when I do that. Let's see if I can erase it. That kind of erases it. It also looks terrible, but we're going to go with it for right now. Okay. So how do we actually make predictions about what exact angle it's going to end up at? Well, that's where we get Snell's law. Snell's law is what relates the index of refraction to how far it turns exactly. Okay, so let's draw a diagram. Okay, we have medium 1 out here, and the ray comes in just like this. Okay, so this is going to be angle 1. Okay, And it's going to come down here into medium 2. So something else. We don't know what it is. And I want to know, what does it do when it comes down here? It's going to go in some direction, maybe closer, like this, but maybe further away, like that. I'm really not sure which it's gonna do. So just for sake of argument, let's say it comes down here and it's closer. So that would mean that this is a big N and this is a small n. Remember that n stands for the index of refraction. So this will be theta 2. Okay, we get this right here, which is Snell's law. N1 times the sine of theta 1 equals N2 times the sine of theta 2. Okay, so let's do a quick example of this. Okay, let's say that we have light traveling from, what should we do? Let's do air into glass. Okay, actually let's do a vacuum into glass. Okay, so this is going to be a vacuum. And when I say vacuum, I obviously don't mean the thing you clean your carpets with. I mean something that there's no material. It's completely empty. Okay, and it's going into glass down here. And let's say that this starting angle is, just to make it easy, 30 degrees. Okay, so let's plug in the values we know. What is N1? Well, it's the index of refraction of a vacuum, so that's 1. The sine of the angle 1. Okay, so it's coming in at 30 degrees. Plug that in right there. What's N2? Well, it's glass. So if you happen to recall from the other page, the index of refraction of glass is 1.5. So now we're going to need to solve for sine of theta 2. So we get the sine of 30 divided by 1.5 equals the sine of theta 2. I'm going to need a calculator. If you guys have a calculator, go ahead and try and calculate that. Turns out I didn't bring a calculator home, so let's try and do this. Do it on my phone real quick. Sine of 30 divided by 1.5. Alright, so for that I got this side simplifies out to be 1/3. And that's equal to the sine of theta 2. So in order to solve, we're going to have to take the arc sine of both sides. In your calculator, that looks like sine -1 of 1/3. So that's what we'll type in. What is the arc sine of 1/3? Arc sine of 1/3. Just give me the answer in radians. So let's convert that to degrees. 19.5 degrees. 19.5 degrees is theta 2. So notice that it came in at 30 degrees, but once it hits glass, it goes into glass at 19.5 degrees. So just like we thought that it was going to come in closer to that perpendicular, it's going to turn in to the glass at a smaller angle. That is what actually happened. It went from about 30 to about 20. So that makes sense. And that is Snell's law.